In the case of I squared, so again thinking 1 squared plus 2 squared plus 3 squared plus 4 squared, etc. Here, this turns out to be n plus 1, 2n plus 1, all over 6. And again, if you don't remember these formulas, there are nice proofs to show that these formulas work. They require some mathematical induction. Most of you who took a pre-calc class would have seen these. If you didn't, that's okay. Like I said, you just need to know how to use these formulas. And then for I cubed, again, cubing each of my numbers from 1 to n, this is just going to be n squared, n plus 1 squared, all over 4. Okay. And then, of course, the last one that we're going to look at is if I have sums or differences of different functions in terms of my expression. These work a lot like our derivatives and integrals. I can just separate these. So I can look at the sum from 1 to n of f of I plus or minus the sum from 1 to n of g of I. Okay. And so those are the formulas we will use to evaluate our definition of our definite integral. Okay. And so another thing to keep in mind is in order to use this definition, I need to be able to find pieces of this. So as I said, when I have a small finite number of subintervals, it's easy to find my delta x and my f of x sub I, because I can basically look at the interval and break it up easily, and then take those values and just plug them into the function. Now again, if I'm doing infinitely many of these, I don't want to write out that list. That's going to be impossible to do. And likewise, it's going to be hard to determine what the endpoints are at each one so I can get that function value. So here we want to generalize it. Okay? So an example here would be, let's just find the delta x, the x sub I, and the f of x sub I for some different functions on some intervals. And these are all going to work very similarly, and that's why I've given you two different examples here. In the first case, I'm looking at a function on an interval that starts at 0. Okay? In this case, because I'm going from 0 to 2, to find my delta x, basically I just want the length of the interval. Okay? The length of the interval is going to be 2 minus 0. And then for the subintervals, I'm just going to take that length and divide it by how many subintervals I want. In this case, there's n of them. Okay? So here, my delta x is just going to be 2 over n. Okay. For the x sub I, it means I want to take a point in each subinterval that we just found. So if my subinterval each has length 2 over n, then I can use this value to determine where the next subinterval starts. Okay? And I can just basically take and say that my x sub I is going to look like 2 over n times I. So if I is 0, then I'm at the start of my interval. Okay? If I is 2, then I'm in 4 over n, which is going to be 2 subintervals away from 0. If it's 10, I can think 20 over n, which again is going to be 10 subintervals away from 0. Okay? So if it starts at 0, it's enough to say that my x sub I is just my delta x times I. And again, my delta x here, we can think of, if this is a and b, it's b minus a over n. Okay? And then for my function, so my f of x sub I, well, I'm just going to plug 2i over n into my function. So here this is going to be 3 minus 2i over n quantity squared, or I can simplify that to 3 minus 4i squared over n squared. There's my f of x sub I. And again, all I'm doing there is I'm taking the value that I found here and plugging it into my function. Okay? So if my interval starts at 0, I can use this information here. If my interval does not start at 0, I'm still basically doing the same things. It's just that things are going to get tweaked a little bit. Okay? So if a does not equal 0, so for example, this case here, I'm looking at the interval from 1 to 4. Again, I just have some function. Doesn't matter that it's not quite the same as the one previously. My delta x, I'm going to start the same way. It's still going to be b minus a over n. So I'm going to take 4 minus 1 over n to get the length of my interval, length of my subintervals. Okay? So my delta x doesn't change any. Okay? My x sub I is going to change a little bit. Because if we think about what we said the last time, if I plug in 0, I want it to be the start of my interval. Well, in this case, if I plug in 3i over n and I plug in 0, I get 0, but that's not in my interval. So here, I have to think x sub I is going to be the start of my interval plus my delta x times I. I know I'm kind of writing off the side of the board here, so let me just move that over a little bit. X sub I is going to be the start of my interval plus my delta x times I. Okay? So in this case, start of my interval is 1, and my delta x times I is just going to be 3i over n. So again, here I can see if I put in 0 for I, then my first point is going to be the start of my interval. It's going to be at 1. If I put in 3, I can see I'm going to get 1 plus 9i over n, which is going to be 3 subintervals away from 1. Okay. My f of x sub I, same thing. I'm just going to take that and plug it into my function. So we'll get 3 times 1 plus 3i over n quantity squared plus 1 plus 3i over n for the x minus 1. And again, before I go on to use my summation formulas or write out that limit, I'm definitely going to want to simplify this. So that means multiplying out. So foiling, we'll get a 9i squared over n squared plus a 6i over n plus 1. All of that will be times 3. Notice over here the 1's will cancel. And so we'll get 27i squared over n squared plus an 18 and 3, so 21i over n plus 3. So there would be my f of x sub I. In this next example, we're going to look at using that limit definition to find the area or the value for the definite integral. Okay. So in this example, we've got the integral from 0 to 2 of x cubed minus 4x dx, and we want to use the definition to evaluate it. Okay. Again, what that means is the first thing I need to figure out is what is my delta x, what is my x sub I, and what is my f of x sub I. Okay. So this one, again, if I look at my interval is from 0 to 2, which means that my delta x is going to be 2 minus 0 all over n, or 2 over n. Okay. My x sub I, again, because my interval is starting at 0, I know this is going to be 2i over n. And so to get my f of x sub I, again, I'm just going to take this and plug it into my function to get the function value within each subinterval. So we'll take 2i over n and cube it minus 4 times 2i over n. And again, I can simplify this, and we can see that I'm going to get an 8i cubed over n cubed minus and 8I over n. Okay. So here, my integral from 0 to 2 of x cubed minus 4x dx is going to look like the limit as n goes to infinity, my sum, I equal 1 to n, of my function times my delta x. Okay. Now, a lot of this problem is algebraic, so I'm going to just need to simplify this algebraically, take my summation, and then take my limit. Okay, so first thing I'm going to do is just multiply my f by my delta x. So we'll get a 16I cubed over n to the 4th minus the 16I over n squared. And then I'm going to use my summation properties to rewrite. Okay, so remember, for the summation properties, it says if I've got a sum or a difference, I can break those apart. Okay, so this is going to be the sum, I equal 1 to n, 16I cubed over n cubed to the 4th, minus the summation I equal 1 to n, 16I over n squared. Okay. Now 16 and n to the 4th, those are pretty much coefficients in terms of my functions in terms of I. So those can be moved out front just like all of our other properties that we have. So I can say this is 16 over n to the 4th times my summation for I cubed. Likewise over here, the 16 over n squared can be brought out, and then I can just look at my summation for I. At this point, this is where I'm going to use my summation formulas to get everything in terms of n. So here, my limit as n goes to infinity, I'm going to drop the summations and rewrite them in terms of their expressions. So the 16 over n to the 4th gets carried along. The summation of I cubed, we said, is n squared n plus 1 squared over 4. And then the 16 over n squared is going to be multiplied by our summation for I, which was n plus 1 over 2. Again, probably want to simplify before I try to take my limit. In here I can see n squared times n plus 1 squared. When I go ahead and multiply that out, I'll get a 16 n to the 4th plus a 32 n cubed plus a 16 n squared all over 4n to the 4th. Same thing over here. When I multiply out, we'll get a 16n squared plus the 16n all over 2n squared. Again, to take my limit, well, these are nice rational functions. Nice thing about rational functions, if I'm taking the limit as it goes to infinity, is I only have to consider the dominant terms. So for this first one, my dominant term is 16n to the 4th over 4n to the 4th. And likewise over here, my dominant terms are 16n squared over 2n squared. The other terms are negligible as n goes to infinity, because these are going to tell me where it's going to go. And notice in these cases, I can cancel out the ends. So I'm looking at the limit as n goes to infinity, 16 over 4, which is 4, minus 16 over 2, which is 8. Says the limit as n goes to infinity of negative 4. And if I look at that, well, there's no n's left, so that tells me my value is negative 4. So there's the value of my integral over that particular interval from 0 to 2. Okay. Again, this was a nice example because in this example, I'm starting with an interval that begins at 0. And so finding my delta x and my x sub i's are fairly straightforward. In this next example, we're going to look at the same type of thing. We're going to evaluate a definite integral, but this time it's not going to start at 0. So here we're looking at one that starts somewhere else. Whether it's a positive number, a negative number, doesn't matter. Just something that doesn't start at 0. Okay? So in this case, again, we're going to start by finding our delta x, which again is basically the length of the interval divided by the number of subintervals. So here, our length of our interval is going to be 3 minus 1. Number of subintervals, again, is just n. So 2 over n will be our delta x. For the x sub I, again, in this case, we're going to look at delta x times I, but we have to consider the start of the interval. So in this case, it starts at 1 plus our delta x times I. Okay. To get our function value, we're again just going to take this and plug it back into our f of x. So here we can see we'll get a 1 plus 2i over n quantity squared, 3 times 1 plus 2i over n plus 4. Again, probably want to simplify this before I try putting it into my limit. So we'll get a 1 plus a 4i over n plus 4i squared over n squared. So foiling that out, plus 3 plus 6i over n plus 4. Combining terms, so as our f of x sub I will be 4i squared over n squared plus 10i over n plus 8. Okay. So our integral from 1 to 3 of x squared plus 3x plus 4, it's going to look like the limit as n goes to infinity of our sum, I equal 1 to n, of our function times our delta x. Okay, again, we want to start by simplifying that. So we're going to go ahead and distribute that 2 over n. So we'll get an 8i squared over n cubed plus 20i over n squared plus a 16 over n. Now again, we can separate. So we'll separate these out into 3 separate summations. Pull our coefficients out front. So we'll get an 8 over n cubed times our summation for I squared plus a 20 over n squared times our summation for I plus the 16 times our summation That's backwards. 1 over n times our summation for 16. So there's our constant. Okay. Again, for these three summations, we can now use our formula. So we have the I squared formula, the I, and the constant formula. So here we'll get 8 over n cubed, multiplied by our summation for I squared, which is n plus 1 times 2n plus 1, all over 6. Oops, it's a plus. 20 over n squared times our summation for I. And our 1 over n times our summation for 16. Okay. Just like the last one, we want to clean this up some so that we can take our limit. So here again, I want to multiply things out. So multiplying out here and then multiplying by 8, I'm going to get a 16n cubed, plus we'll get a 24n squared, plus an 8n, all over a 6n cubed. For the middle terms, we'll get a 20n squared plus 20n, all over 2n squared. And for that last term, 16n over n. Okay. Again, we can look at this as a limit of some rational expressions. So we are going to pull off the dominant terms. So our dominant terms here are the 16n cubed over 6n cubed. Here it's the 20n squared over 2n squared, and, well, 16n over n. Again, like the last one, I can see that things will cancel out. So limit as n goes to infinity, we're looking at a 16 over 6 or 8/3. 20 over 2 or 10, and 16, which we can simplify. It's going to be a 26 which we can take the limit of a constant, it's just that constant, and we can see when we multiply we'll get an 18, get that wrong, we'll get 26 times 3, which is 18, and 1, 78, plus an 8, so it'll be 86 over 3. A couple of things to keep in mind when you're doing these. So again, the first is you have to be careful on your x sub I, and it'll depend on whether or not your interval starts at 0 or some other number. Once you've simplified and gotten your function, remember your summation formulas, and there again it's just knowing which ones of those to use. On an exam, I will give you the summation formulas, you just need to know how to apply them. Okay? The other thing to keep in mind is once I get down to this limit stage and I'm actually starting to take the limit, notice in every one of our examples we no longer have n's after this point. Okay? If you are getting n's that are not canceling out, that means you made a mistake in your algebra somewhere. Okay? At this point, once I cancel out and I'm looking at the dominant terms, everything should be a number. and these will always work out to be some number, as we've said before for the definite integral. Okay. On an exam, you're going to be expected to do at least one of these. This will show up on the final as well. Okay. And again, the way you're going to know to use this method, as opposed to some of the other methods that we're going to use, is that it's going to say use the definition. So it's going to have that definite integral in there, meaning there's limits on it, but it's going to tell you specifically to use the definition.